Okay, good evening. Welcome to
MathForKids number 69.
MathForKids number 69. Today we're going to see if there's something bigger than countable infinity. So something that you can't count with like you can count the integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to infinity. Okay, so we learned that countable infinity is sort of, kind of how many integers there are.
You can count up to it.
Yeah, you can just keep counting and you'll get to countable infinity. So anything you can sort of pair with the integers. And we learned some surprising things over the last two videos. The last video was MathForKids number 68, and the video before that was called FamilyMath number 3. We learned some surprising things. One is that the even integers were the same, had the same infinity as the normal integers, right?
All integers.
And then we learned the squares have the same infinity. And then we learned the really surprising thing that the rational numbers, that the fractions, like 3 halves and 10 sevenths and 127 over 3, if you list out all the fractions, you still get the same infinity. And so people wondered, is that it? Is that the infinity? Can you give me that eraser over there on the table?
Sure.
So this guy named Georg Cantor started wondering, what if we could write down all of the numbers? So remember how we found a way to list the fractions?
Yeah.
With that funny little square argument? So Cantor said, what if we just started listing the numbers? And so number 1 was the number, 1.342971 ... writing them out in decimals. Do you know what that means?
Yeah. Writing
them in decimals? Okay. And number 2 was maybe 23.618047. And then number 3 was... Sure, you can do this one. What do you think number 3 could be?
54.61845570.
Okay. And so...
so on.
And so on. Actually, I'll do one more. Number 4, I'll make it, I don't know, some funny number like 3.141592665. Some number that nobody's ever thought of before.
Yeah, no one's ever studied.
Yeah. So, etc. Okay. And then what Cantor wondered is, if you made this list, like just same kind of list that we made with the fractions, would you get all of the numbers? And then he came up with this clever argument showing you'd always be missing some number. Okay?
Mm-hmm.
So here's how the argument goes. We're going to form a new number, and it's not going to be on our list. Even if our list goes all the way down
to infinity.
We're going to form a new number, and we're going to call that new number, I don't know, x.
X.YWZ.
Okay. And all we're going to do is we're going to start after the decimal. We're just going to say 0 point. And so we're going to go to every single one of our numbers. Okay. Maybe I should make one of these numbers start with 0 point, just so you don't think I skipped anything starting with 0 point. Okay. So, and we're going to say, for our first digit here, if this digit is a 1, we're going to make it into a 3. And if it's not a 1, we're going to make it into a 1. Okay?
Yep.
So here's our rule. If 3, then make it into a 1. If not 3, you remember how you make that little squiggle? Not 3?
Yeah. Half of it.
Make it into a 3. Okay? So for the first digit, we're going to look at the first digit of the first number. That's a 3. So we make it into a 1 for our number. Okay. For the second digit, we look at the second digit of the second number. And the second digit of the second number after the decimal is a
1.
Okay, so that's not a 3, right?
Yeah.
So we're going to make it into a
3.
Okay, for the third digit, we're going to look at the third digit of the third number. Now that's an 8.
8's not a 3.
That's not 3, so we're going to make it into a 3. Okay. For the 4th digit of our number x, we're going to look at the 4th digit of the 4th number. Hey, that is not a 3. So we're going to make it into a 3. And this number is going to go on forever. And then Cantor said, this number is not on the list anywhere. And so, how do we know that? Well,
how is it bigger than infinity?
Well, hold on a second. No, it's not that. Well, I'll get to that in a minute. We thought we had a list of all the numbers, and then we just made a new number that wasn't on the list. And here's how we know this number wasn't on the list. You ready?
Yeah.
Because this is the tricky part. When we compare this number with every single number, it's different than the first number in the first digit after the decimal, because we've turned the 3 into a 1, so we know it's different there. So we know this is not equal to this number. It's different than the second number because the second number's second digit after the decimal is different. Because remember, it was a 1 and we made it into a 3?
Yeah.
It's different than the third digit, the third number in the third digit. Because that digit wasn't a 3, so we made it into a 3. So if we go down the line, it's different than the nth number in the nth digit. Because if the nth number's nth digit was a 3, we made it into a 1, and if it wasn't a 3, we made it into a 3. So this number is not anywhere on the list. So we thought we had a list of all the numbers. And then with this clever little construction, we found a number that's not on the list. Okay? So maybe what we could do is we could say, oh, well, we'll just put this number on our list and we'll make this the 5th number on our list. We'll push all the numbers after 5 down and we'll just make this the 5th number, 0.1333, whatever, maybe 0.131133, like that.
Yeah.
But now we can do the same thing all over again and we can find a new number.
Whoa.
That's different. So no matter what, so what Cantor figured out is no matter what list of numbers you have, you can always find numbers that aren't on the list.
Oh.
And that means that no matter how you make your list, you never get every single number. So this countable infinity isn't big enough to list all the numbers. It's big enough to list all the integers, but it's not big enough to list all the numbers.
Whoa.
So it's bigger. The infinity that lists all the numbers is bigger than the infinity that lists all the integers. Isn't that amazing?
It's totally amazing.
It's totally amazing. And there's a really interesting unsolved problem in mathematics is that nobody knows for sure how big this infinity is. Okay? No one knows exactly for sure.
There were approximations.
Well, Cantor also showed how to create new infinities from smaller infinities, but they don't know for sure how big this infinity is. That's pretty interesting. Now did you have one other question about this?
No.
No? Okay. Well, so there you go. This is called the Cantor diagonal argument because you take the numbers down this diagonal. And it's a really, really neat argument.
I'm gonna take this number.
Yeah. Well, we didn't do that number yet. It's a really neat argument, and it shows that infinity for the integers isn't big enough to list all the numbers. So you need a new infinity.
To infinity and beyond.
Right. This is beyond infinity. That's really cool. All right. Good job today, honey.